Okay, so now that you've gotten a little taste of organic structures and how they act, now we can look at a little something called stereochemistry. So stereochemistry is going to be all about the orientation of organic structures. What direction are they facing? What is the orientation of the various atoms within the molecule? You know, what's going on with the exact structure between different types of molecules? And this is all things we're going to be concerned with when dealing with stereochemistry. Ultimately, in Gen Chem, you're not going to touch on this very much. It's a huge topic in organic chemistry. It's a gigantic topic. But in Gen Chem, you're primarily going to be focused on the concept of isomers. And isomers are essentially going to be when you have molecules that are similar, but they are oriented differently in some way. So similar molecules with different orientations. So first up that we're going to talk about is the constitutional isomer, which is also known as the structural isomer. So for the constitutional isomers, this is when you're going to have two different structures for the same molecular formula. For example, the formula C6H12. There's over a dozen ways to draw this particular orientation of 6 carbons and 12 hydrogens. So each of the various ways that you can draw this would be a constitutional isomer of this particular molecular formula. Let's look at a few of them, for example. So one way you could draw this would be the cyclohexane molecule. So 6 carbons, single bonded in a ring. So this would be one way to draw this. Another way to draw it would be something like this, with a double bond in the middle there. So 6 carbons with 12 total hydrogens, but drawn completely different. I'm sure you would agree that this cyclohexane is a completely different orientation to this double bonded structure down here. But they both represent the same molecular formula. So that's going to be the name of the game with constitutional isomers. They're going to share the same molecular formula, but their structures can look radically different to each other. When you're judging whether something is a constitutional isomer or not, just count the number of elements that are there. Count the number of carbons, count the number of hydrogens. If they're the same for both of them, then they're constitutional isomers of one another. If they aren't the same, then they're not constitutional isomers. That's about as complicated as that gets. So now let's look at another type of isomer known as the cis-trans isomer. And this is when you're going to have a double bonded carbon with 4 different groups coming off of the 2 different carbons. So a great example of this would be the following. So here we have 2 carbons double bonded, which is really the landmark that you want to look for cis-trans isomers. If you don't have this double bond here, then you're not dealing with a cis-trans isomer. So this double bond in the middle is really what you want to look for. And of course, after that, you want to look for the 4 different, well, not 4 completely different, but the 4 things bonded on the outside. So 2 going up, 2 going down, double bond in the middle. That's what you want to look for if you're judging if something is a cis-trans or not. And ultimately what you want to look for is what side of the double bond are your elements on. So here, if we use this double bond as like a wall between the 2 different sides, here you can see that the hydrogens are on the same side of the double bond, and the bromines are on the same side of the double bond. So because they're on the same side, we would call this the cis isomer. And the reason it's called the cis isomer is that cis is the Latin word for same. and each of these elements is on the same side as each other. So the bromines are on the same side, the hydrogens are on the same side. That would make this the cis. Whereas the other one here would be the trans isomer. And that's because really all you have to look at here is you have a bromine on this side and you have a bromine on this side. So the bromines are on opposite sides of the double bond, which would make this the trans. Trans is Latin for across. So the bromines are across from each other in respect to the double bond. And like I said, for cis-trans isomers, you always want to look for this double bond in the middle with two groups going up and two groups going down. And that would be sort of your calling card for cis-trans isomers. So now we get to the last one, which is a little more spicy than the other two. So enantiomers. Enantiomers are really tricky sometimes, and I think they're the most confusing out of the three types that you learn in Gen Chem. So when it comes to enantiomers, we're really focused on one concept, and that's chirality. So chirality is when you're going to have a carbon, so we'll draw a carbon here, with four different things bonded to it. So let's say one thing bonded to this carbon would be hydrogen. Let's say another thing bonded to this carbon is chlorine. Let's say another thing is bromine. And let's say another thing is an alcohol group. So, very weird structure going on here. A lot of weird stuff going on. But this would be a good example of a chiral carbon. And chiral comes from the Greek word for hand, which is chires, and that means hand in Greek. And so chiral is the word we use in chemistry. It's because hands are non-superimposable. If you take one hand palm down and place the other hand on top of it palm down, you'll notice that they aren't imposable. They're not, perfect alignments. They're opposite of each other. It's just like a mirror. When you look in a mirror, what you see is the opposite of what's actually there. So, for example, what's on the right appears to be on the left, and what's on the left appears to be on the right. And that's what's going to be true with chiral carbons when it comes to the enantiomers that form from chiral carbons. Really what you want to look for with a chiral carbon is four groups coming off of it. It doesn't have to be individual elements. It could be the entire rest of the molecule. So in many cases you'll see huge molecules with chiral carbons where the entire rest of the molecule is considered one of the bonded groups. So really what you want to look for is four different bonded groups. Here we see that pretty simply with these four different things going on here. We have a hydrogen, chlorine, bromine, and an alcohol coming off of this one carbon. And this would be our four different groups. So this is a great example of a chiral carbon. Some things you want to look for: double bonded carbons will never be chiral carbons. Only single bonded all the way around carbons are considered chiral carbons. So the first thing you want to look for is four single bonds. If your carbon doesn't have four single bonds, it's not going to be chiral, it's not going to have an enantiomer. So if we wanted to look at this particular molecule here, and we wanted to draw an enantiomer of it, we would draw something like this. This molecule here would be an enantiomer of the first molecule, because the elements are placed in different locations on the carbon, but they end up being mirror images of each other. They are not superimposable, which means you couldn't place one of these over top of the other one perfectly. What they are is mirror images of each other. So this molecule here would be an enantiomer of this molecule here, where these chlorines are mirrors of each other, the bromines are mirrors of each other, and the alcohols are mirrors of each other. but you couldn't stack these two molecules on top of each other perfectly. And that's really the definition of an enantiomer. You have to look for a chiral carbon, and you have to ensure that that chiral carbon's enantiomer is a mirror image of the original molecule. And that's where you'll get your enantiomers for your stereochem with chiral carbons. And again, you want to make sure that your chiral carbon is indeed chiral before you draw an enantiomer of it. So that was just sort of a breakdown of the three major isomers that you learn in Gen Chem. If you go on to take OChem, you'll learn about these in a lot more detail. And when I say a lot, I mean an extreme amount of detail. So if you want to learn more about these, please take organic chemistry. You'll learn all about them there. But in Gen Chem, you just kind of get a taste of them.